In this section, we will discuss the kinetic molecular theory of gases. And this comes from the idea that gas molecules have a certain amount of kinetic energy. Understanding the kinetic energy of a gas is going to be important because it's going to be related to its pressure. Remember, we've defined gas pressure as the pressure exerted by a gas on the walls of a container due to collisions. So these collisions are going to be affected by the kinetic energy of the gas. The more kinetic energy the gas has, the more energetic collisions it's going to make, and this is going to have an effect on gas pressure. Overall, inside of the kinetic molecular theory of gases, one of the more important ideas is that it derives an equation that allows for the velocity of a gas to be calculated. And the velocity of the gas is important because it has an effect on the kinetic energy of the gas. We gain this equation where Rms is the root mean square speed of a gas. And the root mean square speed is the square root of the average of the squares of the speeds of all the molecules in the sample. That might seem like a lot, but really the idea is at a given temperature, gas molecules can be traveling at different velocities, and what we want is a way to have an average velocity for a sample of gas. Inside of this equation, T is the temperature of the gas in Kelvin. In this case, we're using the other value of R, which is 8.314 joules per mole Kelvin. Remember, I like to call this the energy R because it involves joules. So here we're looking at kinetic energy or involving kinetic energy, so it makes sense to use this R value. M is the molar mass of the gas, but what's kind of important to remember is that the units on the molar mass cannot be grams per mole. Usually we report molar masses in grams per mole. In this case, we must report the molar mass of the gas in kilograms per mole. The reason why is that the unit joule in our constant R has the units of kilograms meter squared per second squared. So even though you don't directly see it, it is hidden inside of the unit of a joule. So the molar mass of the gas must be reported in kilograms per mole. When we look at this equation, we can make some conceptual conclusions. And in general, if the temperature of the gas is increased, what happens to Rms? So as the temperature increases, Rms also increases. So the basic idea is that when you take a gas and you heat it up, the gas molecules tend to increase in velocity, and then this is going to increase the pressure. So that's something else that we've seen previous in this chapter, that when you raise the temperature of a gas, the pressure of the gas also increases. Another conceptual idea we can make is if the molar mass of the gas is decreased, what happens to the Rms? And here, because it's inversely proportional, as the molar mass of a gas decreases, the Rms increases. This says at a given temperature, the smaller the gas molecule, the faster it goes. And from this we can gain some understanding about the world around us. Inside of Earth's atmosphere, there's not a lot of helium. And the reason why is helium is a very small gas molecule and it travels fast enough to escape Earth's gravity. It's actually able to obtain escape velocity. Some of the other larger gases like nitrogen and oxygen cannot do that, so they are stuck to the planet Earth by Earth's gravity and their lack of being able to obtain a sufficient velocity to escape Earth's gravity. So here's a classic question where we ask to calculate the Rms speed of oxygen, and that's O2, molecules at 25 degrees C. So we use this equation. We want to plug in our variables. The temperature is given as 25 degrees C. We need to convert that to Kelvin. The molar mass of oxygen is 32 grams per mole, but we need this in kilograms per mole for our equation. So you divide by 1,000. R is a constant, and then we plug the values in. And in this case, remember, raising something to the power of 1/2 is the equivalent of taking the square root. So we take the square root of this whole part of our calculation, and when we're done, we find that the Rms of oxygen molecules at 25 degrees C is equal to 482 meters per second. And what's kind of interesting is that you will find that this number that we just calculated is actually related to the speed of sound. So the speed of sound is directly related to the speeds of the gaseous molecules inside of Earth's atmosphere.